All right, you should be ready to go.
So we have linear programming, and the first part of the slides I'm just kind of going to skip are the ones Joseph did, and they're posted to Canvas. And this is Kim's part. Can she? Oh, shoot.
Is Kim with us?
Can you hear me now?
Yes.
We can, yes.
There you go.
Thank you. I'm so sorry. I was just able to log on. So my name is Kim Wade, and I will be going over sections 7.4 and 7.5 from the textbook. So in 7.4, solving Flair Furniture's LP problem using QM for Windows, Excel 2016 and Excel QM, we look at tools that are available to us to solve some of the more complex and larger linear programming problems. In today's modern world, computers are able to solve these problems for us. Most firms and organizations these days are adequately equipped with and have access to software that is capable of solving these larger linear programming problems. We've truly come a long way in the past 50 years. 3 examples of software that we can utilize to solve LP problems include QM for Windows, Excel 2016, and Excel QM. Some of these programs may be slightly different from one another. However, the approach and elements are basically the same. Once you have some experience with using them, they become like second nature. You begin to recognize how, when, and where to maybe make some necessary minor adjustments, etc. When using QM for Windows, you'll first want to select the linear programming module. Once you're on the page, you will specify the number of constraints and enter the number of variables. There's a place in the upper left corner where you will choose whether the objective is to be maximized as in profit or minimized as in cost. Once these are specified, the input window will open. Okay, next you will enter the coefficients for the objective function and the constraints. You'll also make any other adjustments here, as in renaming variables, names or constraints, etc. Next slide. Once you've entered the data and just before the problem is solved, the QM for Windows, QM Windows linear programming input screen reflects numbers such as values of the variables and the objective function value, which is the profit, as shown here. At this point, you will click the Solve button, typically located up on the top right area of the menu. Then choose Window and select Graph if you want to display the output for the graphical solution. This will include the corner points and the problem. The Excel add-in solver is the next valuable tool we'll look at. Before using this, you will need to create a spreadsheet with specific information, formulas, and calculations related to the problem. Steps that are involved in creating this spreadsheet include entering the coefficients, constraints, and RHS, which stands for right-hand side's constraint bounds for each constraint. You'll need to designate what cells will be used for the values of the decision variables. Then, using the coefficients for the objective function from step 1 and the cells containing the decision variables values from step 2, enter a formula that will calculate the value of the objective function. Using the coefficients for the constraints from step 1 and the cells containing the values of the decision variables from step 2, enter a formula to calculate the value of the LHS, left-hand sides, of each constraint. You should continue to construct your spreadsheet, entering data where applicable. Symbols used here, such as less than or equal to symbol, are simply for reference and not used by solver. The cell addresses for the values of the variables are entered into solver in the by changing variables cell box. Go to the Data tab in Excel 2016 and click Solver. The Solver Parameters dialog box opens. Follow the instructions provided here and enter all constraints. Then click Solve. There are additional options available at this point, like adding constraints or including sensitivity reports. If an optimal solution is found once you have clicked on Solve, the solution will be entered into your spreadsheet. Excel QM is the third tool that I'll discuss, and this one, in my opinion, is the Cadillac of them all. The output is formatted automatically very nicely and is very professionally looking. In Excel QM, from the alphabetical menu, choose linear, integer, and mixed integer programming. Enter the program title, the number of variables, and the number of constraints. Mark whether it is a maximization or minimization problem. Click OK, and then a spreadsheet will be provided for data input. The solution is shown under Results at the bottom. This software provides helpful hints too as an added benefit. The next section, 7.5, talks about minimization problems. Linear programming problems deal with either maximizing, which is usually considering profits, and minimizing, which is typically referring to the cost of an objective function. Here we're going to focus on the minimization. Smaller problems with only 2 variables can be solved graphically by using either the corner point method or an isocost line approach. Here we want to find the values of the decision variables, for example, x1 and x2, that yield the most minimal cost. Let's take a look at the example provided in the textbook. The holiday meal turkey ranch is considering buying 2 different brands of turkey feed and blending them to provide a good, low-cost diet for its turkeys they are raising. Here we see the information that we'll need for consideration of our problem, like the cost of each ingredient for each brand of feed, along with the minimum monthly requirement that's needed per turkey. In this scenario, we will make our two variables represent the following. So X1 will be the number of pounds of brand 1 feed purchased, and X2 will be the number of pounds of brand 2 feed purchased. We will minimize the cost using the following formula. Equal to 2x1 plus 3x2, and subject to these constraints. Prior to solving the problem, you'll need to be sure to remember that the third constraint implies that the farmer has to purchase enough of brand 1 feed to meet the minimum standards for the C nutritional ingredient. So this will need to be taken into consideration. We'll solve for the best blend of brands 1 and 2 to buy per turkey per month. So say, for example, if the ranch houses 5,000 turkeys in a given month, it will need to simply multiply the X1 and X2 quantities by 5,000 to decide how much feed to order overall. Another thing to take note of is that for this problem, we're dealing with a series of greater than or equal to constraints. So these cause the feasible solution area to be above the constraint lines, hopefully as seen on the next slide. We plot the three constraints to develop a feasible solution region for the minimization problem. Note that minimization problems often have unbounded feasible regions. In this case, there are three corner points, A, B, and C. For point A, the intersection of the ingredients C and B constraints, the following equations are used. 4x1 plus 3x2 is equal to 48, and x1 is equal to 3. You'll want to substitute 3 in the first equation so that x2 will equal 12. For point B, x1 equals 8.4 and x2 equals 4.8. For point C, x1 equals 18 and x1 equals 0. Now that we have our figures, we can now evaluate the objective function at each corner point. The minimum cost solution is to purchase 8.4 pounds of brand 1 feed and 4.8 pounds of brand 2 feed per turkey per month. This yields a cost of 31.2 cents per turkey. So using the isocost approach, the isocost line method is analogous to isoprofit line method that we used for maximization problems. As with isoprofit lines, we need not to compute the cost at each corner point, but instead draw a series of parallel cost lines. The lowest cost to touch the feasible region provides us with the optimal solution corner. I apologize that my diagrams are not showing up, but in this page, it would show an example of the isocost. Okay, there it is, the isocost approach. And you can see up in the upper right corner is the feasible region shaded. And then using QM for windows, there is also an example. It did not show up. And then also for, okay, and then there's an example for QM for windows, how that solution looks, and also for the Excel 2016 solution. And then these would be your formulas used for Excel 2016.
Thank you, Kim. And so before, Campbell, I don't know if you made it on yet. Is Campbell on here? Oh, no.
I don't think so.
Okay, I'll just go to my part then. Okay, and I've gone over and just kind of do a few examples of how to solve different linear programming situations in Excel. And so the first one is an example here of Bob Bell's 40th birthday, where he's going to prepare some pre-prepared drinks for the party, and he's going to make 5 different kinds of drink, and then he has how much each of the drink will consist of the different ingredients. And then you formulate using LP and then solve it in the LP software as solved it in Excel. So first you want to find the objective. That's the first step you want to do once you're doing a linear program. And in this case, it's to mix ingredients in a way that makes the largest possible number of drinks in advance. And then you want to look at what constraints you have. So there can be, the constraints we have is there's no more than 52 ounces of bourbon can be used, no more than 38 ounces of brandy can be used, no more than 64 ounces of vodka, and no more than 24 ounces of dry vermouth can be used, and no more than 36 ounces of sweet vermouth can be used. And then it shows here that a Shanxi consists of 1/4 of bourbon, 1/4 of vodka, 1/4 of brandy, and 1/4 of sweets. And it kind of shows what everything, each one will consist of, and each drink consists of 4 fluid ounces. And then you would write that out. So we establish like the variables for each liquor, and just kind of the same thing, but then calling the first one X1, which would be the Shanxi, which is X1, and then X2 and X3 and X4. And then we would insert it into an Excel form. So we have our variable, which I kind of just wrote above so you can see which one is what. And then our solution is going to be blank. And then the amount of drinks, we're just going to put, since it's there's not really a cost to it, but you want to maximize the amount of drinks, I just added 1 for each drink. And then you want to find the total amount of drinks. This is some spelling mistakes, sorry, drinks. And then down here in the constraints, I have that 25% of bourbon is going to be used in the Chelsea's, and then 25% of brandy, 25% of vodka, and then 25% of sweet vermouth. So you have your constraints in here, and then you have the left-hand side here where you insert the formula being the sum product of our solution, and then that will be one of our things you put in the sum product, and the other one would be of the bourbon here. And then we have on the right hand side, we have that it has to be less than or equal to 52, because that's the max amount we have available. And you could do the same formula all the way down here. And then afterwards you've done all these, you will go in to use the solver, which is in the right top corner of Excel. If it does not come right away when you go into your Excel, you might have to go under your add-ins and add it. And I also know a few computers are struggling with getting the solver to work. And so once you use the solver, it will come out with the result here, and we can produce 104 Chelsea's, 20 sweet Italians, 26 bourbons, and 57 Russian martinis. And that, as we can see, is below, is under the amount of what we have available, is staying under or equal to the amount of ounces we have available of each drink. And then just here showing how much we're producing, the total of 207 drinks. And I have a second example too, which is Jeannie Reid is the general manager for the NRG Inc. And the company is producing two types of electric generators, which are BR54 and BR49. And then orders have received a production schedule to be set up for the next 3 months. So we're going to make the production schedule for the next 3 months. And here are some of the factors we want to be aware of. The generators may be produced in 1 month and stored until the next month. However, there is a cost of holding these in inventory, which is 1% of the cost per month. The BR54 cost is $80 each, and the BR49 cost is $95 each. The company can produce a total of 1,100 units each month. And currently, beginning our production schedule, there are 50 units of each type in the warehouse. And at the end of October, the company would like to have 100 units of BR54 and 150 units of BR49 in stock. And then the demand for each production is given over here on the side. So in August, it's 320 for the BR54 and 450 for the BR49. And then you need to formulate a linear programming to minimize the cost, and how many of each unit should be produced each month, and what is the total cost of the solution. So the first step is when you set up the production schedule, there are several factors that you need to consider. The first is that the company must meet the demand for the two products in each of the 3 months. And also the company would like to have the 150 units of BR54 and 150 units of BR49 in inventory by the end of October. And then there's a carrying and holding fee for the cost of any inventory left at the end of each month. So producing any extra units of either product might not be desirable because the carrying cost assigned is 1% of cost per month. And then the cost for producing each is written out with the 80 and the 95. And then the company cannot produce more than a total of 1,100 units per month. So I wrote down the constraints where it says 3 demand constraints. So there's 1 constraint for each month in demand for BR54. There's 3 demand constraints, 1 constraint for each month for BR49. And then there's 2 constraints, which is 1 for the BR54 and 1 for the BR49 for the inventory at the end of October. And there's also a constraint for the BR54 and BR49 for the beginning inventory. I forgot to write that down. And then there's 3 constraints for the maximum production capacity each month. And so this is the decision involving how many units of each of the 2 products are produced in the 3 months. There will be 6 variables. And the objective is to minimize the costs. And there are costs associated not only with the units produced, but also with the inventory that is left each month. So we're defining the variables. So AI is the number of units of BR54 produced in a month, and then BI is the number of units of BR49 that's produced in a month. And then the line AI is going to be the amount of units left in inventory, and the line BI is going to line AI, and the line BI is going to be the units of BR49 left in inventory at the end of each month. And for the inventory here, it just says 1, 2, 3 for August, October. But when you write it out, you actually have a 0, 2 for the beginning month, because we're starting with inventory already. And so to minimize cost, it would be the 80 times A1 plus 80 times A2 plus 80 times A3 plus 95 times B1 plus 95 times B2 plus 95 times B3. And then you would have to plus that with 0.8 times the amount left in inventory. And in 0.8, because is 1% of the total cost of each month. So by taking the amount of units that's going to be, so by taking 1% of the cost of BR54, by the end, we're going to have the amount of cost of inventory that's going to be left over of each of these months, and for the BR54. And then we did the same calculation under here for the BR49. So we have that. And then the inventory constraints, I said, a relation among closing inventory this month and closing inventory last month. So this month's production and sales this month. So like inventory at the end of this month is inventory at the end of last month plus the current month's production minus sales. And then if you want to move all the variables to the left side, we're going to have the inventory at the end of last month plus the current month production minus inventory at the end of this month, which is going to equal the sales. And then I have just kind of written out all the constraints here, where A1 minus our inventory A1 is going to be equal to 320, which is the demand for August. And then for September, it's going to be our inventory from last month plus our demand for this month minus the inventory for this month. And it's just kind of written out here. And then we have the max amount for production per month, which would be that A plus B is have to be less or equal to 1,100 for August, and then A2 and B2 for September, and A3 and B3 for October. And then all other variables has to be greater or equal to 0 since it's a non-negative constraint. And inserting this, we're going to have the variables up here, and notice that we have the line A0 and we still have the cost down here in the minimum cost because we're starting with inventory. So that is going to have, since we're carrying that over, it's going to have the inventory or holding cost. And then we have our right hand side data, which is our demand. And then it's going to, and then in our 14, we're going to have the amount of inventory we want to have by the end of October, the amount of inventory underneath we want for B54, and then underneath for BR49. And then below those, we have our 250s, which is the inventory beginning we have for each of the two generators. And then all the way in the bottom, we have our production constraints, which is the 1100 for all 3 months. And then the ones in here just shows that for our left side calculation, for total cost first, we're going to have to take our sum product of our solution and of our minimum cost. And then in the left hand side for August BR54, we're going to have sum product of our solution and the row we have right here in between with the 1 and the -1 in it, which is going to give us the formula we used on the other side here with the demand for BR54 in August being A1 minus inventory of A1. And then the second would be A1 minus plus A2 minus inventory A2, which can be seen that we have the 1 under A2, we have the 1 under inventory A1 and a -1 under inventory A2. And that kind of just goes all the way down through. And then in the bottom, we have inventory beginning under inventory 0 and A0 and inventory B0. And then once you click on the solver, this is what will come up. And so the first one up here, and I apologize, my solver is in Danish. It is the first up here where it says $P, $5 is our objective, and that will be our total cost. And then we will choose that we want it to be minimum because we want to find the minimum cost. And then we have $B, $4 to $0, $4. That is our variables. So that's the changing variables we want them to be able to change. So that is actually the row of our solution. And then in the box down here, we can add our constraints. So in this case, we have that the P20 to P22 has to be less than or equal to R20 to R22, which is down here showing that our left-hand side over here has to be less than the 1100, which is our production constraints. And then for the constraint right underneath, it just shows that our P8 to P17 has to be equal to our R8 to R17, which is our left-hand side up here for the demand constraint has to be equal to the right-hand side, which is the demand we have and constraints we have. And then you will choose that you have to make your variables non-negative. And then you want to choose the simple LP or simplex LP, and then you choose solve. And then it's going to solve it. And it's going to give you the data here, and it's going to give you a total cost. And just so you can see here, so our demand for inventory A0, which was our beginning inventory, is going to be 50. The amount of inventory we're going to have for our generator 1, the BR54, is going to be 190 in August, 130 in September, and 100 in October. For our second generator, the BR49, we're going to have our beginning inventory of 50. And then we're actually going to have 0 in both August and September. And that's why I haven't written them down. And then we're going to have 150 in the inventory by October. And the amount of each we're going to be producing is for the BR54, we're going to be producing 460 in August, 680 in September, and 470 in October. And for the BR49, so our other generator, we're going to be producing 400 in August, 420 in September, and 630 in October. And the other variables are equal to 0, and the total cost is going to be 267,028. And looking at mine, the numbers is a little bit different because I did do a mistake. I accidentally had the one by the inventory switched around before I took this picture. And that causes 2 of my solution variables to be off. But once you switch those 2 around, it's going to give you the right answer. But I had a lot of trouble with getting it to actually show up after. So I just kind of wanted to explain that's the mistake that happens. And this shows how little it takes for a mistake to happen. So it's really important to make sure that you double check all of your formulas you put in, where you put the numbers, that the numbers are represented correct. Because otherwise you end up having it vary a little bit off. But once you change these 2 around, like I have them now, is correct, it's going to give you the result we have here of the total production. And then I have an example more if anyone has questions that I can go over. It's the same example that's in the book for the Excel solution, if anyone has any questions.
That's a lot of information. So I wouldn't blame anybody if they did not have questions at this point, because at least for my money, linear programming is probably the most complicated topic that we cover in this course. And so, it takes some while to wade through the material that's presented in the textbook and other sources. And it takes even longer to adjust or absorb that material.
Yes, and just for in the textbook, whenever you are looking at the linear programming, for the example I have here, which is the production scheduling for Greenberg motors, for when they show the formulas you have to choose for the different things, they have accidentally, instead of choosing R5, written F5, which is one of the minimum costs, but you always want to use the total cost for your objective. Just in case that doesn't cause any confusion when people go through it, because that was one of the things I had to kind of sit and figure out.
All right, very good. Thank you. I am going to stop the recording at this point.